Let's get started. Welcome back, everyone. Today we're going to be talking about a few things. But we're going to start with reviewing some stuff about the best rank K approximation. So this will be some things that we sort of covered at the end of the last lecture on Wednesday, but we went over it sort of quick, so we'll review some of that. So next we will get into the relationship between the eigen decomposition and like eigenvalues and eigenvectors, how those relate to the singular value decomposition, which we've been talking about. And so hopefully the main takeaway is that they're really roughly worrying about the same objects, at least when you start with data, and that when you're starting with the data matrix, then you don't have to worry about a lot of the weird conditions you may have learned about eigenvalues and eigendecompositions. So then everything is nice. And then the third thing we'll get to is the power method, which is an algorithm to actually compute these things. So far we just said there was some magic command that you could run inside of Python or any other language, and we'll look a little bit under the hood. There's a really long history of methods to compute these things. The power method, I think, is the simplest version and the one that captures the core contents. There are some small improvements on this, but I don't think those improvements are extremely consequential. So just work at this one, and then probably the rest of your life, you'll probably just kind of call this as a pre-optimized function. Okay. So after today, you can start the rest of your life, is what that means. Okay. So before we get started, just review the schedule. So a little bit, we're all the way down here. We're looking at the dimensionality reduction, and we're getting kind of close to the end of the semester. Homework 5 is out, and quiz 5 is on Wednesday. There'll be one more homework and quiz after that, so we're getting close to the end. So homework 5, I posted this. So I posted early this afternoon. It's due next week, Wednesday. And so it's going to be just on dimensionality reduction. The first 2 questions don't ask you to look at any actual data, but forces you to kind of think about what's going on with the SVD, and then what's going on with the relation between, this question 2 is about relation between the power method and the eigen decomposition SVD. You'll have to kind of reason about these things. If you're really familiar with this stuff, this might be really straightforward for you. If you are not as familiar, I hope both of these questions, there are some that make you think a little bit to kind of force yourself to kind of understand some of the properties under the hood. The third question is going to be about looking at some actual data. I grabbed 200 words from an embedding of them in 50 dimensions. This is kind of a precursor to how these large language models work. I grabbed it from one of those. The words have 4 categories of words, and they're labeled inside the file. So when you download them, you'll get a file, but it will have the first few columns will tell you kind of what the word is and what category and subcategory it is. And then you're going to use the SVD and then PCA, which we'll talk about on Wednesday, to plot this down into 2 dimensions and kind of visualize them. And you'll see that based on this embedding, you should kind of expect the words from different categories should wind up in kind of the same place. All right, so if you color code them, when you plot them, which you don't have to do, but be kind of fun to try and do that, you should kind of see them having nice structure to them. Okay, so that's homework 5. It's posted now, so you can get started on that. I think you should be able to get started on almost all of it, basically everything after today's lecture. There's a little bit, the very last question, which will cover after tomorrow's lecture. Okay, great. So let's get into it. Okay, so let's start by reviewing. Okay, the rank K approximation. Okay, so we're going to start with a matrix. Well, we will start with our input is going to be a matrix A, which is an N by D, right? And we're going to assume, as we usually do, that N is greater than D. You could do everything kind of backwards if D is greater than N, but it's easier to think about this way, I think, or at least we're being consistent. And so what we're gonna do is we're gonna start by thinking about this singular value decomposition, right? So I'm gonna run some svd command on my input A. I'm gonna get out matrix U, S, and V transpose, right? And so this is going to be so that I can write A is equal to U times S times V transpose as this matrix multiplication. Again, I like to think of these as these rectangles so I can keep the dimensions straight in my head, right? So there's going to be N rows and D of the columns in this matrix A, okay? And when I do the decomposition, I'm multiplying it by a orthogonal matrix U, which is a square, so it's N by N. Then I'm going to have a rectangular matrix S, but this one is only interesting stuff on the diagonal. And then another square orthogonal matrix V transpose, right, which is going to be smaller. That one's only D by D. Okay. And so we decomposed it into here, and the interesting parts of this are kind of the through lines of the left. This will be uj, the left singular vector, a corresponding singular value, and the row in V transpose, this would be Vj. This is the right singular vector. Okay, and so yeah, so okay, and our goal here, okay, so with the goal with the kind of rank K approximation, okay, is going to be, the goal is going to be a matrix A prime, which is also going to be the same dimension, N by D, so I can directly compare them to each other, except I'm going to enforce that the rank of A prime is going to be equal to K, and we're going to say that, or I'm going to say less than or equal than K, but will typically be exactly K, and K is less than D is less than N, right? So we want something that's going to be a small rank approximation. You remember what rank of a N by D matrix is, where N is larger than D? How do I determine the rank of the matrix? How did we talk about this before? Yep. Yep, it's the number of linearly independent rows or columns. I can check either rows or columns, it'll give the same answer. And so it can be at most D, right? The rank of an N by D matrix can be at most D, okay? And I'm going to allow the rank of A prime to be less than or equal than K in case that the rank of my input is already smaller than D. But typically we'll assume the input matrix is going to be full rank. If I'm observing data, it's sensed with some noise or some properties, and it's very hard to get a low rank input data matrix if N is much larger than D. Okay, so we're typically assume the A input is full rank. Now we want to get an approximation that is a smaller rank. So the rank kind of, it says there are not a lot of linearly independent columns, at most K of them, okay? And so this goal is satisfied by a matrix we call AK, Okay, and it's going to be the arg min of all the matrices A prime that have a rank of K. Okay, that's that of the cost function A minus AK with a norm. This is going to be a matrix norm, and this matrix norm will be the Frobenius norm or the 2 norm. Okay, so it can be either, and they're going to give the same answer. Okay, the Frobenius norm we'll walk through a little bit more what these mean on the next slide or two. But there are 2 different ways I can define this, and I want to find the rank K matrix that best approximates my my input matrix. Okay, and so basically there's well-known answer that AK, I can use the singular value decomposition to construct this matrix. It's J equals 1. I'm going to sum over these terms, which is the singular value times UJ VJ transpose. And as a reminder, this is an outer product. So this term is an N by D, but is rank 1. Okay, so when I take 2 vectors and take their outer product, I get an N by D matrix. This is an N-dimensional vector, it's an D-dimensional vector, and I've got the transpose right, so it's an outer product, and it gives me an N by D matrix, right? So each pair of entries between these 2 vectors, I multiply them, and that goes into the corresponding cell in this matrix, but it's only rank 1. Okay, so when I do an outer product of 2 vectors, I get an N by D matrix, but it's only rank 1. Now I'm scaling it by saying how important is this rank 1 matrix? These are unit vectors, so they have no scale information. And this singular value tells me how much to scale it by. These are in decreasing order, so I take the first K. Those are going to be the most important ones, and this will give me the best rank K approximation. Okay, and so now I can be reminded that I could have recovered the entire matrix by taking J equals 1 up to D of the same expression. Right, so if I do the same thing, but I go all the way up to D here, right, then I'm going to recover the entire matrix A. This will recover it exactly up to numerical error. And the numerics on this have been optimized. They're pretty good, so it will basically recover it. And what that means is that A minus AK, if I subtract these, this is what I'm going to take the norm of. A minus AK, this is going to be the sum again of J equals, for J of sigma J, UJ, VJ transpose. But now I'm going to start with K plus 1, and I'm going to go up to D. Okay, so the terms in this one cancel the terms in the full reconstruction, and I just get the leftover stuff. This is sometimes called the tail. Okay, so this is sometimes called the tail of the matrix. Is kind of the less interesting part. This would be called kind of the head, like a snake. This is the head, and this is the tail. And I choose at some point K of the snake to chop it, and all the good stuff's on the head, I guess, for the most interesting stuff. Okay, this is the best rank K approximation. Let's go a little bit more into what these different norms mean, and this will kind of help give a remind or give more intuition about what these representations mean. Again, this is partially review from last time. Okay, let's remember what is V1. This was, remember, this was the first right singular vector. All right, the first right singular vector. And how did I define what this was? How did I get the first right singular vector? This was the arg max of all vectors in RD. and I have this hard to optimize condition that it has to have a norm of 1. Okay, if I and I want to maximize the quantity A times V, let's say, squared. Okay, and remember this quantity, I can write this as I equals 1 up to n. This is the sum now over all of the row vectors, AI times V squared. Okay, so it's my, if I take this norm of the dot product of a matrix with a vector, that's the same as taking what I'm doing is, if I just did A times V, I'm going to get out an n-dimensional vector, right? If I do just this inner operation here, this will give me a point in Rn, right? So A times V will give me a point in Rn. When I take the norm of that, well, I'm gonna, the squared norm of that vector, I'm gonna take all those entries in that vector and square them and add them up. Well, that's exactly what this red expression is doing, right? All those entries in the vector is V times the first row, V times the second row, and I could write them down and I add them up. Well, the norm is just doing this all at once, okay? So I can think of this as the norm. So the first right singular vector is the one that is optimizing the maximum norm of projecting all the data onto it. Remember, the dot product is the projection, right? So what this is saying is that there's some data. And again, we're still assuming these are probably centered at the origin, and that I'm choosing a vector V1, okay? V1, and I'm looking at projecting all of this data onto this vector. Okay, and then I'm taking its length from 0. Okay, so some of the values are going to be positive, some of these are going to be negative. Let's say this is A1, then the length of A1, this is going to be A1 dot V1. Okay, so the length of it, well, it's a negative value because it's going in the negative direction. But the length of A1, the projected dot product, is the negative value. How far from the origin? Here, I'm taking all these, I'm squaring them, and I'm adding them up. Like, what is kind of like the variance of this? I want to find the direction where the data has the most variance, assuming it's already been centered. So that's what this is doing. V1 is the direction that maximizes this. So that's the first right singular vector. That's what it's doing. Right? And remember, we're trying to get a best projection that captures the most variation. This is the first best projection that captures the most variation. Okay. And so now, this is good. This kind of explains what the first direction is doing, right? In the right singular vector. We're slowly working up to an algorithm of how to compute this, but this intuition will be helpful. Okay. The next thing we want to look at is what is the first angular value, right? Sigma 1. So sigma 1, the first singular value, this is going to be equals to A times V1, just this norm. The first singular value is just going to be the norm of A times V1. Well, I already computed the norm of A times V1 squared, so I just take the square root of that, right? Right, so I can write this as the I equals 1 to n, AI V1 squared, all under square root. Okay, that's fine. That's not necessarily super helpful towards doing it. Another way of thinking about this is it's equivalent to A the spectral norm of A, the 2 norm of A. Okay, the 2 norm of A, the spectral norm, that's what it's often called, is, what was this? This is one we defined in the linear algebra review, and it had this really weird, hard to imagine what the definition was. Hopefully this definition will now make more sense. It was the max over all directions U in RD, such that U had a norm of 1 times a U. Right, so this is what the spectral norm was. This was the definition of the spectrum. All right, sometimes you write 3 lines if that's the definition. Okay, so it's not only equal, well, but that's what I maximized up here to get the first right singular vector. Okay, so that's why it gives me the spectral norm of A, and this kind of gives a sense of the spectral norm of A is actually just this first right singular vector, so maybe this is not such a weird sort of concept here. Okay, so now kind of connecting this together with the norm here. Okay. Okay, now what is a bit more interesting to think about here is what's going to be sigma j squared. All right, where this is going to be the jth singular value, right? Or this jth singular value squared. This will be the jth singular value squared. Okay, so the jth singular value squared. Okay, so this is going to be equal to AVJ squared, right? Where this is the jth right kind of the singular vector. Okay, so this helps a little bit. The jth singular value I can again get by taking the jth singular vector, multiplying by A, take the norm. Okay, so this part makes sense. But I haven't explained how I get this. This first one was defined as the one that maximizes this variance. This one is a little bit, in general, let me look at V2, and VJ will be similar. V2 is going to be the, not jth, the second right singular vector, okay? And it's going to be the unit vector V that maximizes AV, okay? So this part is the same, but V1 needs to be equal to 0, okay? But it's orthogonal to the first right singular vector, okay? So if I, V1, right, is here, right? So it has to be orthogonal to the first right singular vector while it maximizes this, okay? And so it's a little bit harder to define what exactly it means, right? I have to define it in a way that's recursive, okay? It's dependent on the previous singular vectors. Remember, all the singular vectors have to be orthogonal to each other. And so V2, I want to maximize that direction, the most variance, but it has to be orthogonal to the first one. And when I talk about VJ, VJ has to be orthogonal to the first J minus 1 of them. And then of everything that's left, it has to maximize it. Okay, so this is what we'll see this come across in the algorithm, and that we're gonna compute V1 first. and then we'll have to compute V2 after we deal with V1. We basically take V1, we remove all the effect of V1, and then we run the algorithm again to get V2. And then we remove all the effect of V2, and then we run the algorithm again on everything that's left. We have to run it recursively in this way. There are other ways to do this, but this is the main way of doing it, okay? The other consequence of that is that this is hard to interpret what this means, okay? What is the second right singular vector? Well, it's not like a second mode of variation that is individually meaningful. It's something that maximizes, but it's really dependent on the first one. And so if you look at like the fourth singular vector, what does that mean? Well, it's something that's kind of an important direction, but it really depends on the choice of the first three. Okay, and so I see a lot of people try and read meaning into these second and third and fourth and fifth singular vectors, and they're really kind of sensitive to whatever the first ones are. Okay, there are some cases where this makes sense, where you have these really separated components that describe something. This happens with like, if you look like the resonant frequencies of things, and then you have like these, each kind of in some spectral space, each resonant frequency has this very own distinct meaning, and it comes from something, and they all mean something individually. But quite usually, after the first one, they're hard to interpret. Okay, so this I would say, this is hard to interpret by just by itself. So it's hard to say what this means by itself. The first one is very clear what it means. It's the direction of the most variance, assuming it's been centered. But the second one is hard to interpret by itself. But in combination with the first one, I can say these are the two directions, the span of a two-dimensional space that captures the most variance. They make sense in conjunction with the first K of them. Okay, so the rank K approximation is really the right way to think about them, not individual jth singular vectors. That's kind of, those very often don't mean something by themselves. And reading too much into that will often lead you to some fallacies of over-interpreting something. Okay. Okay. Great. Okay. Let me say one more thing about A sub k. Okay. A sub k, remember, we could write this as j equals 1 up to k of sigma j u uj vj transpose, right? I wrote it up in this way. There's another way to write this as a matrix. This is A sub k. I can write this as the product of three matrices. This would be called U sub k, S sub k, and this would be, I have to get the dimension of this right. Actually, no, that was okay. This is S sub k, and then this is going to be VK transpose. Okay, so the dimensions here, this one is going to be, this is D, N by D is A sub k. Remember, this lived in our N by D. This is going to be N by K. This is going to be K by K. And this one is going to be K by D. Okay, so what we're going to get here are, these are, okay, these columns here, this is U1 through UK. These are the first K left singular vectors. Okay. The diagonals here are going to be interesting. These off diagonal are going to be 0. And this is going to be the first k singular values. Okay, so I'm only going to store the first k. It's only a k by k matrix. And now the rows here are going to be V1 up to Vk. These are going to be the first k right right singular vectors. Okay, so I've only used the first left k, the first k left singular vectors, the first k singular values, and the first k right singular vectors. What I had done before with this decomposition of A was that I had made the matrix much larger than before. And so the decomposed pieces were now kind of these blown up representations. They had this nice orthogonal structure, which is nice to talk about mathematically, but it's not really a compression of this. This, if k is less than d, this should be much skinnier than this matrix, right? This one is just k values, and these are only k by d. So this can be a much smaller representation of what's going on here to get back the best rank k approximation. Okay, so I can also think of this by trimming these U, S, and K matrices, U, S, and V matrices to just the important parts, and then I reconstruct them. I can also think of it this way, the equivalent representation. Yeah. Yeah, the S was there. It was it's the one that's almost all empty, and the bottom part, remember, is all zeros. So I've thrown all those zeros away completely, and then I even threw away some of the singular values in there. Yep. Great. Okay, so this is another way of thinking about this. Okay, so this was, okay, so that's about how we can get the best rank k approximation. Hopefully this gives more insight. Hopefully you've seen maybe a little bit of this before in linear algebra. Now we've kind of gone to a bit more. We want to talk about the relation with eigen decomposition working towards the algorithms. And to this, we need to talk again about our square matrices, because to define eigenvectors, I need a square matrix M, and we're going to think about this as D by D. Okay, so we're going to go to square matrices M, and now I can define the an eigenvalue of M will be a lambda j, which will be just a real value, and an eigenvector will be Vj, which is going to be a vector in Rd, and they're going to satisfy this kind of really cool equation where if I multiply M, in this case on the right, by the vector Vj, I'm going to get back lambda j Vj, and usually I assume that I've normalized Vj, so it's going to be a unit. Okay, so this is what eigenvalues and eigenvectors are. I start with the square matrix, and then I get back a matrix. I need a square matrix because if I do M times a vector, I want a vector back of the same dimension, right? That's been scaled. And in fact, it's the same vector. They're pointing in the same direction. This is what makes these eigenvectors sort of happen. Okay. And now remember what the eigenvectors are, we can recall that the eigen decomposition, this will be like the singular value decomposition. It's called the eigen decomposition. And this is where I'm able to write M is going to be equal to V times L times V transpose. Okay, so again, I'm decomposing M into 3 matrices. The matrices will be as big as M again, so it's not really useful. But let me just remind you what these components are. So if we assume, we're going to assume M, yeah, we're going to assume that M is going to be positive definite. That means that these are all well-defined with real values, and that the rank of M is going to be equal to D. Okay, so we're going to assume positive definiteness of M is going to give us this. And this will mean that we'll be able to say that there's going to be I can represent as a set of D pairs of these V1 lambda 1. This is an eigenvector eigenvalue pair. V2 lambda 2 dot 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 VD lambda D. Okay, I'm going to have these D pairs that are going to have the property that lambda J is going to be greater or equal to lambda J plus 1. So these are in decreasing order. Okay, and I'm going to have Vj dot Vj prime is going to be equal to 0 for J not equal to J prime. Okay, so all the eigenvectors are going to be orthogonal to each other. And the eigenvalues, the lambdas, are going to be in decreasing order. Okay, and now this decomposition uses this matrix V twice. What is this matrix V? This matrix V is going to be storing these eigen vectors as the columns. Okay, so this will be, I'll take all the eigenvectors and I'm going to put them in the columns. So this will be a matrix that's going to be in R D by D. It's going to be all the eigenvectors are going to be unit vectors, and they're going to be orthogonal. So it's going to be an orthogonal matrix. Okay, and then L is going to be a diagonal matrix filled with lambda 1 up to lambda D. This will also be in R D by D. Okay, so this is the eigen decomposition. Then I can take V, multiply it by L, which is the diagonal matrix, and by V transpose again, and I get back M, right? So this is a very nice decomposition. To say in a full generality, if it's not positive definite, then going through all the conditions of when this exists and the properties of it, remember from linear algebra class, can be really complicated. You probably spent some time dealing with special cases. Okay, we're going to circumvent those cases by only starting with nice matrices M. Okay, only starting with nice matrices M, and then we're going to show how to get this eigen decomposition. And to say we'll always have this nice form where I can assume that the eigenvalues are real, and they're going to be real and positive, or at least so at least non-negative, and that the vectors are going to the vectors are going to be vectors in RD. Okay, so how do we do that? We're going to get a matrix M, and I'm going to call this MR. We'll see why it makes sense to call it MR soon, as A transpose A, right? This is going to be a matrix in R D by D, where my matrix A was my data matrix of A n times D. Okay, so I remember I started with the matrix that had n rows and D columns. All of the columns, remember, all the columns were of the same unit. They all kind of captured somewhat the same thing, like a bunch of stock prices or temperature at weather stations, or these these like word embeddings that you will get to play with for your homework. All the coordinates kind of mean the same thing. They're all real values. They can be positive, they can be negative, all that's fine. And I do A transpose A. Okay. So if A is going to be, if A has N greater than D and full rank, then MR is going to be positive definite. Okay. So if I start with real values in R, in A, and N is bigger than D, and it's full rank, so its rank is D, then it's going to be positive definite. Okay. If not full rank, then MR is going to be positive semi-definite. And this doesn't really break things. It just means some of the last few eigenvalues are going to be 0. They're still going to exist. They're not going to be polymatic. They're just some of them are going to be 0. Okay, so even full rank does not cause really big problems. Okay, but for now, we'll just assume that like it's data collected with noise, so A is full rank, and then MR is going to be positive definite. And we want to work with this square matrix. It's D by D because I took a N by D matrix, I transposed it, so it's D by N, multiplied it by N by D matrix, I get a D by D matrix. Okay? Okay. Now, just to remember up here again, we said A was by the SVD was USV transpose. This is the SVD of A. And now I want to look at the following expression, MR times the V matrix. Okay, this is the V matrix, the same that contained our right singular vectors. I want to see, let's expand this and let's see what happens. Okay, I think this is kind of a really illuminating expansion. Remember, MR was A transpose A times V, so I can do this, right? And now I can expand A transpose. What is, I'm going to expand it to this will be A. I'm gonna expand the okay, I'm going to expand A as the SVD. Remember, this was USV transpose, right? That's how I expanded A. When I expand the transpose of A, you do a decomposition and you do a transpose of it. You reverse the order and you transpose everything. Okay, so that means that this is V S transpose U transpose. Okay, so I did MR V and I get V S transpose U transpose U S V transpose V. Okay, it's a lot of symbols here, but hopefully they all make sense here. And what's nice about these is there are going to be two cancellations that are going to happen. First, U transpose U, when I can multiply them now in any order I want. I can change the order of multiplication. Sometimes this is slower, but what it gives me is some cancellation. This is the identity matrix, because this is equal to U inverse U, because when U is an orthogonal matrix, the transpose is the inverse. Okay, the inverse and the transpose are the same thing for orthogonal matrices. So that's U inverse U, and U inverse U is the identity. That's the how I get the identity. Okay, and then the same thing happens here. This is also the identity because it is V inverse times V. Okay, so that means these kind of cancel out. They cancel out when I multiply numbers together and I get one in a product, I can remove that one from the product. These cancel out with each other. Okay, so I can rewrite this as V S transpose S. I have to be a little bit careful here because the dimension, this is an N by N. Okay, skinny version of S that had all the zeros in it. Okay. Yeah, and then that's it. And I have another identity, a smaller D by D identity matrix at the end, but that one I can get rid of both of those. Okay. And this, I can actually simplify this because now I'm going to ignore all the zeros in the S matrix, and I'm going to write this as VS squared, where I'll say the S squared matrix is the diagonal matrix of sigma 1 squared, sigma 2 squared, dot, 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 sigma D squared. Okay, so you still following along here. I bring MR from here. I cancel out the U's, I cancel out the D's. Now S transpose times S. These are really diagonal matrices, lots of zeros in them. All I care about, and the two entries on the corresponding parts of the diagonal multiply by each other, and I just get a single diagonal matrix, a D by D diagonal matrix. Okay. So MR was D by D, B was D by D. I get back a D by D matrix. Great. Okay. Now, what does this say when we think about eigen decomposition? What was happening here? An eigenvalue vector and value is when I took a square matrix multiplied by an eigenvector of Vj, and I got back Vj again scaled by something. Okay, so what this means is that this implies if I look at one column of the V matrix, this must be MR times vector Vj is equal to vector Vj times sigma j squared. Okay. If I look at one column, this is, if I look at one column, I'm going to get this expression, and this implies that Vj is an eigen vector of MR, and sigma j squared is the eigen value of MR. Okay, and so hopefully this isn't confusing. I used almost the same notation, but that means that lambda j is equal to sigma j squared. So the eigenvalues of MR are the singular values squared. There's a one-to-one correspondence here as long as all the eigenvalues are distinct, which let's not worry about that case, right? So all the singular values squared are the eigenvalues. Okay. So the singular values squared are going to be equal to the eigenvalues. And the right singular vectors are going to be the eigen vectors. Okay, so the right singular vectors are exactly going to be the eigenvectors of A transpose A. And the singular values squared are going to be the eigenvalues. Okay, so the singular value decomposition, the eigen decomposition are really looking at the same structure if I'm starting with the data matrix and I get my square matrix out. Okay, so this seems great. So if you're familiar with one or the other, you can kind of transform it to it. Wait, why was it only the right singular vectors? The singular value decomposition gave me right singular vectors and left singular vectors. What happened to the left singular vectors here? Yeah, they kind of got canceled out. Why are the right ones more special than the left ones? What I did here kind of canceled them out, right? Well, I also cancel them out up there. They also, at the top up here, I also canceled them out when I did this. Okay, so if instead I were to create an ML matrix, which was A transpose, this is now in n by n. And now I'm going to have that UJ ML is going to be equal to sigma j squared UJ. Okay, so I can do the same thing. I can do the same sort of kind of analysis if I do A transpose and I get an n by n matrix. And now I've left the left singular vectors exposed and I've canceled out the right singular vectors. Okay, so the left singular vectors, the uj of A are the eigenvectors of ML equals A transpose, and still the eigenvectors of ML equals the singular vector squared. Okay, so I'm still getting the eigenvectors are still the same. Okay, but wait, what happens if n is greater than d? What is lambda j for j greater than d? Right, so now the eigenvectors and I wrote eigenvectors, but it helpfully underlined it for me. This should have been eigenvalues. Okay, so the eigenvalues are defined. I get n eigenvalues. So if n was bigger than d, now let's say d was 10 and n is 20. So what is the 15th eigenvalue? How did this work? What happened here? So now I said these were still defined this way. What happened? I know the first, okay, the first eigenvector is the same as squared, or the first eigenvector, the first eigenvalue is the same as the first eigen singular value squared, right? And that, I'm claiming this is true, but I only had, because d was only equals 10, I only had defined 10 eigenvalues. What happens to the 11th or the 15th eigenvector? Okay, what if A was only rank 8, right? And but I'm in D dimensions. What's the 10th eigenvalue of a rank 8 matrix? Or the 10th singular value of a rank 8 matrix? So it's 0, right? Yeah. So the eigenvalues, I can remember back to this decomposition, right? This green one here, I can reconstruct A by summing these things up, okay? But if it was only rank 8, right, less than D, then some of these things don't matter whether I include them or not. I can stop after the first 8 of them. That would mean that I would just set this to 0. It doesn't matter what these are because I'm adding something that's all zeros. Okay, so when I go back to here, now what is the 15th eigenvalue when n is bigger than d and d is 10? 0. It's also going to be 0, right? So these are then these are going to be 0 for j larger than d. Okay, so it's just, the other terms just are zero and they aren't important. So if I do it this other way, I get a bunch of eigenvalues and then the corresponding eigenvectors, which don't really matter if n is bigger than d. And so that's why it's more intuitive to talk about the right side in this case. Okay, great. But so there isn't anything special about the right side. It was just, that was the one that it was full rank in that dimension. Okay, so let's finally talk about computation. Okay, mathematically, we have all the structure we need. So I want to before I compute the eigen decomposition or the singular value decomposition, I want to talk about how to compute the inverse, assuming I have the singular value decomposition. Okay, in particular, for MR, I want to say that this is in d by d, and it's going to be positive definite. Okay, and why is this important? MR equals A transpose A. Well, if you remember, in linear regression, we did alpha star, which are the parameters we had, were A transpose A, inverse A transpose A Y, right? This was this magical expression that we had, right? And this gave us the optimal parameters for linear regression. We assumed n was bigger than d. We did A transpose A, and we called this inverse. I said, we'll learn how to compute this later. Okay. Well, this is actually what we compute the inverse of was MR. Okay. And so if we write MR inverse, well, this is actually, I can use the eigen decomposition inverse. Okay. And this is equal to V inverse L inverse V, because it's actually the when you do the inverse, you do the inverse of you flip everything and do so you do the inverse here, and okay, so I have to take the inverse of each individual terms. The inverse of V is just V transpose. Okay, so a transpose is an operation I know how to do. L inverse V. Okay, so I just need V transpose L inverse V. Transpose is just a change of the position of things. So this I know the algorithm how to do. Remember now that L is going to be the diagonal of lambda 1 up to lambda D. And so L inverse is just going to be the diagonal of 1 over lambda 1 dot 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 1 over lambda D. So for the inverse, it's pretty easy for if I have a diagonal matrix, a full rank diagonal matrix, then taking the inverse is easy. I just invert everything. It's just like taking a scalar and taking the inversion of a scalar is just dividing by it. Okay, so I just do this on the diagonal. So MR inverse is just going to be V transpose times the diagonal matrix of 1 over lambda 1 dot 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 1 over lambda D V. Okay. So now there's no operations we don't know how to do here. We know algorithmically how to do the transpose and how to decompose it to the diagonal elements and do 1 over those elements. So now we know how to take the inverse of the matrix that we got, assuming we know how to get the eigen decomposition. Yeah.
So if we did, basically if we did that from back into like the SVD, if we did the SVD, we would take the V transpose from that, and then we would, for the lambdas, we would do the square.
That's right. Yep. So if I have A, I can do the SVD. These are now the right singular vectors, and the lambdas are the singular values. Right. So I can compute this from the SVD. So I can either compute the eigen decomposition or the SVD, and I know how to do the inverse. Great. The power method, we're going to now describe how to do the eigen decomposition. We're going to describe the power method. You can get this to work for the the singular value decomposition, but it's easier to describe for the doing the Eigen decomposition because I only need to then define the right singular vectors, not in parallel both the right and the left singular vectors. Okay, so we're going to define this to compute the Eigen decomp. Okay, and if I have a little bit of time at the end, I'll write down a little bit of the algorithm to compute the singular value decomposition, but it's once you get this, you can recover the singular value decomposition if you want to. Okay, so let's describe this algorithm, and it's going to be kind of like gradient descent in that it's going to be an iterative algorithm, and you run it a bunch of times, and it will get closer and closer to the right answer. Okay, so it's going to take as input M, which is going to be in D by D, and it's going to take a number of iterations, and I'm going to call this Q, and this is maybe usually 10 to 20 steps is going to be fine. Okay, it's going to depend. We'll say what it will depend on, but usually we're going to run something for a number of iterations, and I think 10 to 20 iterations should be fine. Okay, so first step, step 0, I'm gonna maintain a vector v0, and this is going to get a better and better approximation of the first eigenvector. Okay, so this will be a vector in Rd. It's going to have the property that v0 is going to be equal, the norm of it's going to be equal to 1. So this is the 0th version of it. I'll write down an index inside the power in parentheses to kind of represent that. And this is going to be at random. It's kind of annoying that you have to pick it at random. Okay, but it has to be a random unit vector. And I'll say a little bit later about why that's a little trickier than it sounds like. Okay, but pick a random unit vector. And this, think of this as a guess at V1. This is the top eigenvector. Okay. Okay. So now it's going to have one step of iteration for I equals 1, 1 to Q. Q is the number of iterations. Let me get this out a little bit better. 1 to Q, so number of iterations. I'm going to run one important step. U I is going to be equal to M times U of I minus 1. Or this is V, sorry. Okay, so I'm going to take this vector, and I'm going to take the original vector. So this initially is V0 multiplied by M. I get V1, and I iterated Q steps, like 10 to 20 steps. And I'm going to do this, okay? And then we just return the answer. V1 is going to be VQ after Q steps, and I make sure to normalize it. I may not be normalized at the end, so I'm going to do just normalization. And this will be the first eigenvector. Okay, so this is the algorithm. So this is the whole algorithm. Well, gives me the first eigenvector. Okay, and then I'm going to factor this out. Okay, then I'm going to then, so yeah, so I will so I will come back to that slide. But if I do a power method of M, this will give me V1. So then I do M, let's say 1 is equal to M minus let me okay. So we'll do V1 V1 transpose, right? This will be a rank actually I want to get the scale of here. So I need to do let's call this X equals M times V1. Okay, so this has the scale. I'm going to say, then I'll say M1 equals M minus X transpose. Okay, so this is going to remove a rank 1 component with the scale information. And now I'm going to get V2 on the power method of M1, and then I'll factor out V2 and so repeat. Okay, so once I have the first eigenvector, this slide has kind of some details to make it work. Once I have the first eigenvector, I'm going to then factor out the component associated with it and then call the power method again on what's left to get the second eigenvector, factor this out and repeat. Okay, so this is kind of some detail, but let's look back at this is the most important. This is the important part of the power method. This will give me just the first eigenvector. Okay, this is V1 here. All it does is it multiplies M by my guess of V1 over and over again, and it keeps getting a better and better guess. Okay, and so you can think of this as one step, right? This simpler version for I equals 1 to Q, I just do U or V equals M times V. Okay? I just repeat this over and over again so I can kind of summarize it as just this one step. I'm repeating this over and over again. And how many steps do I need? I need Q equals the number of steps is larger if lambda 1 divided by lambda 2 is small. Okay, so the number of steps is going to depend on the ratio between the first and the second eigenvectors. Okay, if the first eigenvector is really big compared to the second one, it will converge very quickly. If the first two eigenvectors are similar to each other, then this will converge more slowly. Okay. Again, most times in practice, like 10 to 20 iterations is probably enough, but it will depend on the ratio between the between the eigenvalues. I think I said eigenvectors before, but the ratio between the eigenvalues, if the first one is much bigger than the second one, that means it will converge more quickly to the first one. If it doesn't, each one of them represents a direction. And if they're about similar importance, it'll converge more slowly because it won't know which one to pick. I'll try and give a little bit of intuition with this, with the demo in a couple minutes to wrap up. Okay? Yeah.
So for this, is M a matrix that we're given, or is it something that we would get from just our data being the M?
Yeah, so either you can call this on any sort of positive definite matrix, and this will work. If it's not positive definite, some weird stuff might happen. But if I get A, I can create A transpose A, and I can get M.
Okay.
I could also replace this step here by A transpose A. Okay, so I can just, instead of having A, I can multiply B times A, then multiply by A transpose. Doing that would also be. So I can replace M by A transpose A, and the algorithm will work. Okay, I'm going to try and analyze this a little bit to explain why this works. Okay, for a couple minutes, and then 5 minutes, and then I'll show a demo to kind of explain what the mathematics is going on. Okay, so we remember that M we can write as J equals 1 to D, as lambda J, actually we'll write it this way, as Vj lambda J Vj transpose, right? This is kind of we wrote a similar thing for the singular value decomposition. This is from, remember that it's equal to V, L, V transpose. That's the eigen decomposition of M, okay? And what we can think of as getting the V we're getting at the very end is going to be M times some random V0 times another matrix M. Okay, the output of this times another matrix M. Okay, so it's just this expression where I'm multiplying by M over and over and over again. If I unroll this loop inside the inner loop, and so this is equivalent. Now, if I multiply them this is from right to left. But if I did from left to right, I would instead get M to the power Q times this, times this V here. Okay. And so that's why it's called the power method, because it's like I'm taking the matrix M to the power Q. It's equivalent. This is usually a much slower. Doing matrix multiplication is slower than matrix vector multiplication. So I do it the way I described it. Okay. Let's look at what is M squared here. Remember, M squared, I can use my eigen decomposition. Is this, that's what M squared is, okay? But remember, I can now cancel this inner part here. This is the identity. So this is equal to V L squared V transpose. Okay, so M squared is V L squared V transpose. And in general, that means that M to the power Q is going to be V L to the Q V transpose. Okay, so really all this MQ is doing is, if I have the eigen decomposition already, now I don't because that's what I'm computing, but if I did, I just have to take the diagonal eigenvector matrix and take this to a power. Okay, now let's look at what happens if I have lambda 1 equals to 10 and lambda 2 equals to 2. What happens when I take these to the third power, right? Or if I do M1 squared equals to 100 and lambda 2 squared equals to 4. Lambda 1 to the cubed equals to 1,000. Lambda 2 cubed equals to 8. Okay, so what's happening to the ratio between them as I'm taking them to larger and larger powers? The larger thing, the further away from 1, is growing much more rapidly. 1,000 over 8 is much bigger than 10 over 2. This is the ratio of 5. This is the ratio of about a little more than 100. Right? So the ratio is growing a lot. Okay? And so that means in the limit, as Q goes to infinity, then this will be V lambda 1, 0, 0, 0, V transpose. Basically, if I were to normalize them, and I normalize them, then this one is going to totally dominate. It's bigger, and all the others are going to go to kind of zero. So I've normalized. So, and remember, I normalize at the end. Sometimes it's smart to normalize inside this loop. Depends on how you analyze it. Okay. Okay, so if I normalize them in between, then it's going to just the first one. And what happens is that everything will end up, the only thing that matters will be the top eigenvector. Okay, so I'm only going to be multiplying by this top one, and all the rest will kind of disappear. Okay, so I'm only going to get the eigenvector for the eigenvector associated with the first eigenvalue, because everything else proportionally is going to be smaller and smaller. Okay, so let me finish up by showing you a demo, which is linked off of here again. And so this was put together by my former grad student TA a while ago, where we're going to use NumPy. This is the power method. We're going to create a random. Yeah, you need to create U from a random normal distribution, a d-dimensional normal, so it's a random unit vector. You don't want to create it as a random kind of each coordinate is uniformly. You need to create a random kind of random unit vector, so random normal vector. And then I multiply by the input matrix B over and over again, and I normalize at the end. So this was just our algorithm. Okay, so let's start with the small data. We're going to start with A as a random 10 by 3 matrix. And I will then get B in this case, instead of M, is A transpose A. And I can write out, and I'm just computing the eigenvectors so you can see and you can check what these will look like. It's a 3 by 3 matrix, so it's not too big here, but I printed, or it's a 3 by, yeah, so it should be 3 by 3 matrix. I printed everything out here. Okay. The first eigenvalue is 7, about 7, then 0.5, and so on. Why are they not in sort of order? Okay, not so important. Then I'm going to do 4 iterations of this power method. And so I just run it, and I'm going to output the result, and look how, and I'm going to print the result and how close this is. Not V transpose U. Why is this? Okay. What's cool is what I want to show is this visualization here. Okay. And what we're doing is we're starting with this is our data set, A, and we're going to start with a bunch of, instead of a random vector, we're going to choose a bunch of choices for our guess of the random vector here. These are our guesses for the random vector. I'm going to pick evenly spaced unit vectors around the circle. This red direction will be the first eigenvector. Okay. And so now when I run one iteration of the power method, what's happening is that I'm multiplying by that matrix B, which is our square matrix, and it's stretching out along the first eigenvector and kind of shrinking along the second. Okay. And as I multiply it again and again, I can see the old one lighter color in the background, but it's stretching it out more and more. The first eigenvector is getting stretched out. The second one is getting compressed here because it's multiplying by a value less than 1, and the first eigenvalue is greater than 1. Okay, and after, how do I hide this? Go away. Okay. What? Right corner. Great. Thank you. Okay. And where did this go? And so after one more iteration, basically everything is accumulating basically at these points. So it's either the positive value or the negative. And it's depending on my random choice at the beginning, it may give me the negation of the first eigenvector, but the eigenvectors are only unique up to the sum. Okay. So it's really stretching stuff out along the eigenvectors when you multiply by the matrix over and over again. Once I pick the right eigenvector, then it will converge, because multiplying by that vector again will give back the same vector. So once I found an eigenvector, I will stay in that same position. This is why you need to guess at random, because if I guessed and exactly hit on the third eigenvector, it will stay there. And so I might get them in the wrong order if it somehow guesses the third eigenvector. It says I'm converged. I'm going to stop at this one. I factor that one out first. This would be kind of unusual, but it can happen. But the bigger the ratio between the first and the second eigenvector, the faster this will converge to the right answer, no matter where it starts, as long as it doesn't start exactly on one of those other those other eigenvectors. Okay. If you play with this, there's kind of a neat second thing that happens where if I run this for 1,000 operations, it's going to throw an error. Okay, so this will break if I run this for 1,000 operations. And that was because if you don't renormalize every step, then it's going to get some really large values here. It's going to get too large of a value. So if you normalize inside the for loop, this will be more stable. Okay, we'll keep values from exploding. And this version you can run better. So this is a little bit of some of the details that goes into kind of getting this to work at scale. All right, okay, we'll stop here. We're slightly over time, but we got a sense of how the algorithm works. And in practice, you'll just run these highly optimized things that figure out how to stop and when to renormalize and how to kind of save some computational steps.